Hi guys. Okay, so now we are starting this next chapter, reaction rates and chemical equilibrium. So it's a small chapter, but very interesting. So first of all, we will try to understand how do the reactions occur. This is reaction kinetics. And what are the effects of the temperature and concentration on the reaction rate of a reaction. Okay. And then the activation energy, the catalysts, and then what is the concept of equilibrium. And then comes this is I, equilibrium, and then the equilibrium constant, and then the calculations that relate to the equilibrium constant. And the last is the Chatellier's principle, which helps us deviate a reaction from the equivalent if it ends up in the equilibrium state. So let's look at that first of all. How do the reactions occur? So this pertains to the collision theory. This means that the molecules or the atoms are always colliding. And when they're colliding, first of all, keep this in mind that the atoms and molecules are nothing but clouds of electrons, okay? So molecules are electron clouds, okay? So in the beginning, when they collide, or in other words, when they come near each other, so when they approach, okay, when they approach, obviously, and come close, very close, if they come very close, what is going to happen? A repulsion is going to occur. A repulsion occurs because the electrons of one atom and electrons of another atom. So electrons of atom A and electrons of atom B, they are going to repel, because negative and negative charges repel. Okay, so that's one piece. When they approach and if they come very close, then the repulsion is going to occur. Then the electrons of one and the electrons of the other, they cause that negative, because it's a negative charge, right? Even if it's not, even if there is no charge, there is still negative, you know, the cloud will itself be negative because it's made up of electrons. Okay, so there is repulsion. Then how do you make them come close so that they can stabilize and they can make bonds? So that can only happen if they come, you know, at a certain distance. So at a certain distance, when they come close, then the nucleus of one, then if the nucleus of A talks to or attracts the electrons, remember the nucleus is positively charged, nucleus of A attracts the electrons of B, okay, then only the new bond is formed. And in order for the new bond to form, the old bond has to break up first, right? So old bond breaks how? Old bond breaks up if it has certain kind of energy into it. So the old bond breaks after absorbing some energy, breaks after absorbing some energy, okay? And this energy is what? This is called the activation energy. So activation energy activates the whole process of bond formation. So activation energy is something that we supply from outside, okay? Either you heat up the substance, or it just absorbs the heat from outside, and then what happens? The bonds begin to break, and then the new bonds are formed. So in the collision theory, what happens is that the atoms and molecules, they collide with each other. So atoms and or molecules, because the reactions can be made up of anything. So atoms and molecules, when they collide, so it's not just they're just colliding. These collisions have to be effective collisions. Effective collisions are where the new bonds are breaking. The old bonds are breaking and the new ones are forming. So the effective collisions are always going to be at a certain distance, okay, and with a certain force. So when the new bonds, the old bonds break and the new ones form, old bonds break and new bonds form. Okay, and then the attraction is maintained. Attraction between two atoms is maintained or stabilized. How is it stabilized? Because now the nucleus comes into play, okay, is maintained. Okay, by the nuclear pull of each other, by nuclear pull of each other. Okay, so this is one thing. But in order for all this to happen, so one is the collision, just colliding alone, is not going to work, but also orientation matters. So let's just do it on the next page. Orientation also plays a role. So this is the collision. This is what we talked about, is just a collision. And then next is the orientation. So in orientation, what happens? They have to look at each other. Orient, O-R-I-E-N-T-A-T-I-O-N. Orientation means atoms look at each other. Okay, so from what side they are approaching, so in what way, from what angle they are approaching. Like, for example, you have one atom with one side, and then this is the, let's say these are the two sides, and then this is the other atom. So these two, okay. So if they come too close, obviously, if they are just too close initially, if they are very, very close, then there's going to be repulsion. Too close is repulsion. Repulsion if too close. Now, another thing happens is that they try again and they come again, but this time just barely, they are close, but not very close, like not touching. So here they are actually touching, but here we have this guy here, and the other one is just there. So there's just a little spark, So here, and let me just make it a little bit closer. Okay, so just quote. So here that is just a right distance. So they are at the optimal distance, and an optimal distance, the attraction is maintained. Attraction is maintained. Attraction is maintained. And in that optimal distance is actually called a bond length. When they form the new bond, that is called a bond length. So the attraction is maintained, and then what happens is that the new bonds are formed. New bond formed. Okay. Then in the other way, if this guy comes this way and the other one is coming this way, then in that case, no bond is formed, no attraction. So this is no, so they're not looking at each other. So this way, no bond or no new bond is formed. Okay, so if it's from a different angle. All right, so that's the way they've, this is, so in other words, this is wrong orientation. So too close is not good, too far is also not good. And so if this one is over here and this one is very far away, and even though they are in the right orientation, but the distance is too far. So again, no bond is formed. They cannot form a bond. So this is the orientation is very important. So same thing is there with the human beings also. If you look at somebody, only then you greet them, you become, like familiar with them, then you make a new bond, like networking with people. When you create your own network, you create your own, what do you call, friend circle or acquaintances or associations, those things. So that orientation, that looking at another person in the beginning, greeting another person, that is what is going to lead to. If you don't greet or talk, how can you make a bond with another person? So that's the thing. Okay. Next is the energy. Now, fine, just coming close to each other doesn't really help also. It is the right amount of energy, and this energy that is started, that initial energy, that is the energy that starts the reaction. That is the energy of activation. And this energy of activation is all reactions need that energy of activation. And I'm going to put it as EA, energy of activation. Okay, so what is this energy of activation? Energy of activation is the energy that is needed to, energy that can be in the form of like simply mixing things, that is a mechanical energy, heating a little bit, microwaving certain things, reactions, you cook food is in the microwaves, or like even, passing electricity or putting things in the sunlight, right? So all these are different ways that the chemical reactions occur. So we see that the energy of activation, this energy needed to break bonds, first of all. And then this energy, the same, what happens when that energy is released? So the energy is released. So basically, it's the bond energy. Actually, the energy present in the bonds is released. So let's put it here, energy. Sorry about that. Energy that is called bond energy, or let's just put it here, bond energy present inside the bonds of atoms, is released and then transformed to new bonds. Okay, so what does this mean? Okay, look at this. So you have one atom, this is one molecule, A and B. Okay, A and B is reacting with CD, AB reacting with CD. Both of them are mixed together. So first you need to give some amount of energy that is going to break this bond and this bond. And that initial energy that is needed to break the bonds of A, so in this case, let's put it here, AB and CD. Okay, so this energy that is needed, that is called the activation energy. Now, after that, what happens? A combines with D and C combines with B. So what do you produce then? You produce a new molecule in which the transformation has happened. So A and D, a new bond is formed, and we see here C and B. A, that's a different color, D, and this is C, and then B, C, this is C and B. So you see, C combines with B and A combines with D. So remember that. A will have a positive charge, B negative charge, C will have a positive charge, D will have a negative charge. So the A will retain its positive charge and C will, so the plus charged species are written first and then the negatively charged species are written next, okay? So this is what the activation energy is. So in other words, this is the energy bond. So energy of activation is the energy needed to start the reaction. Energy needed to start a reaction. And it's a chemical reaction we are talking about here. Okay. Now, another part of it, some reactions are very slow. And these slow reactions are very, like they will work, but they will take a very long period of time. It could be, several hours, several weeks, several months, and it can take years. So we can speed up the chemical reactions. So it is through the catalyst. So catalyst does what? It speeds up the chemical reactions. How? It speeds up the chemical reaction by different ways. First of all, by either providing an alternate pathways. A reaction is going by XYZ method, and the catalysts will speed up the chemical reaction by reducing that pathway, by providing a shortcut. So, okay, so this is alternate pathways mean a shortcut. So that's how you could speed up the chemical reaction, okay? Next is, they are never a part of the final product. They may take part in a chemical reaction through providing the alternate pathway, through lowering the activation energy, okay? Lowering the activation energy. Sometimes we need to heat a reaction at a very high temperature. Very high pressure is given. So, so we can reduce that, the amount of heat it is needed to break those bonds. We can reduce that by adding a catalyst, which lowering of activation energy. So now we need to provide less energy, activation energy. Okay, so it lowers. And then what else does it do? It can also make intermediates, okay, which are needed to sometimes speed up the reaction. So they do not take part in the chemical reactions, but they do make intermediates. They do not, I'm not going to say they do not take part in the chemical reaction, but they are not a part of the final products, but the catalyst help in making the intermediates. So help in making intermediate reactants or reaction, like something in the middle is needed, help in making intermediates. Sometimes the normal course of a reaction may take very long, but if you have an intermediate, and these intermediates are sometimes like carriers, like carrier molecule, which helps to carry the products, faster. So they act like a carrier molecules, okay? So those are needed sometimes. It depends what the reaction is. So let's just put it here, carrier molecule. Let me put it in a different color. So intermediates could be a carrier molecule or something that is needed, to provide also the catalyst. They also provide surface, okay? They provide surface. Sometimes, especially the gas in which the gas is reacting with the solid. So gas will get adsorbed, surface, provide surface where adsorption happens. Absorption is fully, but ADSORPTION. Adsorption occurs. And what is absorption? Now, I'll show you this thing here. Let us say you have a reaction in which this is a flask, and in this flask you have a liquid, and here you have a bulb or a balloon, or we have a blast of hydrogen gas. going inside the flask or a container, and the container contains this, let's just draw this here. The container contains some liquid, and the liquid is liquid, right? And gas is gas, so two different states. So here, let us say we have, so we bring these hydrogen molecules. So what this catalyst does, this hydrogen is going to, it bolts the hydrogen in such a way that the hydrogen, one end remains outside, the other end remains inside. So the liquid inside can now stay. So in other words, the catalysts, let's put this here, these are generally palladium catalysts made up of, palladium. So this is a catalyst. Catalyst provides surface to hydrogen molecules. And these hydrogen molecules do what? They are adsorbed. A-D-S-O-R-B-E-D. They adsorbed. Adsorbed means what? They are bolted. B-O-L-T-E-D. They are bolted, right? On the surface. They are bolted on the surface. And then what happens when they're bolted on the surface? When they're bolted on the surface, we see that the one end of hydrogen remains on the top, one hydrogen atom on the top, and another hydrogen, so let's just put it here, that one hydrogen atoms, or not even like that, it would be one. And this is another hydrogen atom dangling. Dangling is like hanging, dangling inside the liquid. Okay, so now the liquid molecules can look at it. So this is the liquid here. This is a liquid reactant. So that's how the hydrogens can talk to. So this is how you basically orient. They provide the surface for what? For orientation. So when they orient the hydrogens, then only hydrogen will talk to the liquid molecules, and then how the new reactions are going to form. But if they keep moving around, the gas particles are always very mobile. Remember, the gas particles have very high kinetic energy. So they are very mobile. They're moving all the time. So they won't even look at the liquid. The only way they can do it if they are bolted, and that causes the reaction to occur. Okay. So now liquid reactants react with hydrogen atoms. Okay, so that's the the whole idea of the catalyst. Now let's look at the concept of the catalysts in the effect of catalyst and the activation energy. So effect of catalysts on activation energy. How do you show them? In a graph. Okay, and this is the graph of them. So show them in a graph form. So we have two types of reactions. One is the exothermic reaction. Exothermic reaction, they release heat, and endothermic reactions, you have to provide heat. Endothermic need heat to occur. Okay, exothermic reaction, release heat. Release heat. Okay, so here is, you show them. So exothermic, and let's make this, because I want the same. So copy and paste. Okay. All right, good. Okay, now we have, let us say, this reaction A sorry, this is a reaction where you have A plus B. When they are heated, they form AB, but they release heat. In this case, you have A plus B plus you need to give heat in order to make AB. So that's the difference. So heat is a part of a product here, but here the heat is a part of a reactant. All right. Now, in this case, this is the reaction progress. This is, let's do this here. This is reaction progress, reaction progress, and this is energy, amount of energy you give, energy. Okay, so now let's make it. We have in an exothermic reaction, A and B already are in a very high energy state. Okay, so let's put it here, A and B are a very high energy state. And the reactants, the reactants are in a very high energy state. So A and B are the reactants. So this is the reactant side. This is the product side. This is the reactant side. And these are the product side. So keep that in mind that A, so R is the reactant and P is the product. All right. Now, in the endothermic, the reactants are in a lower energy state, but the products are in a very high energy state. So what happens now? When you give, like in a normal circumstances, you've given some heat, the reaction occurs, the old bonds break, the new bonds form, and the excess heat is given off to the surroundings. So this part right here is the energy of activation. This is activation energy. Okay. Now, since I need space, I'm going to just move it like this. So, so this is the, actually here, transition state occurs. Transition state is where A and B bonds are broken up. So A has absorbed sufficient amount of energy. B also has absorbed sufficient amount of energy. Their bonds break or whatever happens, and then they come close, and then they form AB, and all the excess energy is either released to the surroundings or it remains absorbed with AB. So in the transition state, that is the, so TS, let me put this here also, TS is the transition state. TS, transition, TRANSITION, transition state, and transition state is the bond breaking and bond making. Bonds break and bonds break at the same time in that state. Okay, so that is here, but that only occurs when the substances have absorbed a certain amount of energy, and that is called the energy of activation. So EA is an activation energy or energy of activation. Oh, sorry, I need to make this really small. Okay. Okay, activation energy. Okay, now that is, so let's put this here. This is the amount of energy. This is EA. And this thing is uncatalyzed chemical reaction. This is uncatalyzed. Let's put this here in this color. This is uncatalyzed. What is happening here? Sorry. CATALYZED. This is uncatalyzed when you have not added a catalyst. So uncatalyzed reaction. But a catalyzed reaction, what is that? In a catalyzed reaction, we see that in this case, the energy of activation is lowered. So this is then becomes the catalyzed reaction. The final products are still going to be where they are. The only thing that is changed is this. This is the EA. So this is the catalyzed. So the reaction occurs faster because less energy is needed now to break the bonds. Okay, so that is the energy of activation for the catalyzed, and the other one is the energy of activation for the non-catalyzed or uncatalyzed. So uncatalyzed is, let's just put this here in green. Uncatalyzed is the hump is higher. Okay. So, all right. Next is, so this is these are the reactants and this is the product side. Okay. So this is one thing. Now let's look at the scenario with the what are these called? The endothermic. So these guys will need a lot of energy to start, a lot of energy. The reactants absorb a lot of energy. And let me move this because I need space. And so here, then the new bonds form, the old bonds break. So this piece right here is the energy of activation. And this is obviously the transition state. And that is the energy of activation for an uncatalyzed reaction. So uncatalyzed, C-A-T-A-L-Y-Z-E-D, uncatalyzed reaction. Okay, uncatalyzed reaction, look at that. The energy of activation is so high right here. Large amount of energy of activation. Okay, just give me 1 minute. Okay, so then this is the energy of activation is very large in order to bring a change or in order to react the reactants in the exothermic reaction, in the endothermic reaction, sorry. So the products are formed in a very high energy state. The reactants have a low energy state. So that is why they need a lot of energy to break those bonds, first of all. Now, if you add a catalyst, what happens? This energy of activation is lowered. So quickly the reaction is going to occur. So this energy of activation is, let's make this nice. So this is the energy of activation for a catalyzed reaction. And that one was the uncatalyzed. The green is the uncatalyzed. So let me put this here. This is the energy of activation for the catalyzed. So this is how we show them. Okay, the two reactions. All right, so this is one thing. Next is the concept of rate of reactions. Next is, what is a rate of reaction? So let's see what we covered so far. We covered the collisions. The collision theory is talking about the collisions. It's talking about the collisions, and here we are looking at collisions. And the effective collisions, basically. Okay, so this is one part. This is one part. Next part is the orientation in order for the reactions to occur, right? Then comes the activation energy. Okay, next is the concept of catalysts. And, you know, it's a part of that, but still a little bit more on the catalyst. And then comes the graphs for the exothermic and the endothermic. And then comes last part is the rate of reaction. What is the meaning of the rate of reaction? Rate. Okay, rate of reaction. Okay. Now, in a rate of a reaction, what is the meaning of it? Rate of reaction is the speed with which the reactants are formed. The speed of, the products are formed. The speed of product formation. Now, how can you increase that speed? Or what factors are responsible for the, you know, the product formation? What is it that leads to the change in the concentration? So how do you show this? The rate of reaction is equal to rate of reaction is equal to the change in concentration of the reactants. Change in concentration of reactants and products, basically mostly reactants because we need the products, okay, versus the change in time. Change in time, like how much time? Just like we have the speed at which the car travels, right? It's the same story here. So it's the speed of the product formation and the degradation of the reactants. So what are those factors that are responsible for that? One of the factors is the temperature. The temperature. So what influences the temperature? So when the temperature increases, what is going to increase? The collisions are going to increase. Collisions of the reactants, initially only the reactant molecules are there. So collisions increase. And with the effective collisions, what happens? The energy is exchanged. So whenever the temperature increases, that means the energy, the kinetic energy in the system, it increases. Okay, overall energy of the system increases. When the energy of the system increases, what happens? That energy gets transformed. Remember, the law of conservation of energy. Energy cannot be created, and energy cannot be destroyed, but energy can be transformed from one form to energy. Okay, energy can be transformed. So what is this transformation happening? All this energy that goes either in breaking the bond or in making bonds gets stored somewhere, and that is called the bond energy. It stays within the bond because you want to maintain the shape, the integrity of the new bond. So the bond energy is the energy that is transferred, gets stored. So bond energy is the energy that gets stored in the bonds, okay, that gets stored in the bonds to maintain the identity of the new molecule. Okay, to maintain the identity of the new molecule. And that new molecule is basically the product. Okay, and that identity means the chemical ratio in which the atoms are, that chemical ratio, right? Like, for example, carbon and oxygen is 1:1 ratio, but carbon and oxygen in carbon monoxide, CO2, is 1:2 ratio. Two of them are very different molecules. So that in order to maintain that ratio, we need the energy. In order to maintain the shapes of the molecules, we need the energy. Okay, so all this energy gets, we need the energy to maintain. So bond energy is the energy that gets stored in the bonds to maintain first of all, the identity of the new molecule, which is the product, and that identity is based on the chemical ratios in which the atoms interact, then the shape of the molecule, right? And then comes the properties of the molecule, right? Properties, and then before shape, let's look at the bond length and the bond angle. Okay, the bond length and the bond angle, all that is needed. Bond angle, and that energy is maintaining that. And then, of course, the property of the molecule. Otherwise, the molecule is going to, the properties are dependent on the stability of the molecules. So stability is, it has to maintain that way. It has to stay that way. So that stability is very important. So the properties are dependent on that, on the stability of it. Then we can say, okay, this is carbon dioxide. This is, this is the CO3. And then look at this, CO3 -2. So in this case, it's 1:3 ratio, with a 2 negative charge. So that is a carbonate anion. which is totally different than carbon dioxide. Okay, so that's still so it's to maintain the identity, all that. So the temperature plays a role. That you increase the temperature, the collisions increase, the kinetic energy increase. And with that said, what happens? The temperature increase leads to the increase in the speed. So increase in the temperature, then the speed or the rate of reaction increases. When the temperature goes down, the speed or the rate of the reaction goes down. So this is the reason why when you cook food, when you cook certain things, you heat. Why do you heat? So that the reaction works, the things, it's, you want, for example, you want to bake, food. For example, you want to bake a cake. Let's keep it that way. You want to bake a cake. And the cake will be only done, you heat at like, I don't know how much it is, 450 degrees Celsius, or I don't know what temperature is that, but for 45 minutes. So only then you are going to get the cake, only in these reaction conditions. Okay, so the cake is formed. And you can heat it at whatever temperature you want, but you're not going to the cake which you desire, or the final product. Your final product is a cake that you want. You don't want a burnt cake. You don't want a half-cooked cake. You want a cake that's exactly, so these are the reaction conditions. The temperature affects the reaction conditions. Okay. All reactions have conditions. For example, if you're making an ice cream, so you can heat an ice cream. So when you're making an ice cream, you have to cool it. Okay, so when you cool it, that means that a certain amount of, it is again done at a certain temperature, a lower temperature. Temperature has to go down. Only then that reaction is going to occur. Okay, so that's one piece. Next is the concentration of the reactants. Now, this is very important. So one is the temperature increase or decrease. Next is so in other words, keep this in mind that when you increase the temperature, the speed increases up, so the reaction moves fast. And when you decrease the temperature, the reaction slows down. Okay. Now, that means you will get, and again, it depends on these reaction conditions, what you want. Okay. Next comes the concentration of the reactants. Concentration. Now, concentration is the amount. So, concentration is the amount. So here you have the amount of reactants. Okay, and products also. Okay, so here's the rule that when the concentration, and concentration is shown by square brackets or parentheses. Okay, so when you increase the concentration, and I'm going to just put it here, is equal to CONC raised to the power n. So short form, right? So when the concentration increases, right, you increase the concentration, then the rate of the reaction increases, the speed increases. And when the concentration goes down, then yeah, the speed of the reaction also goes down. Okay, so that's the thing. So that's one of the basic things. Okay, and then now we have the next part, which is the equilibrium. So equilibrium. Now, what is equilibrium? Now, here's the problem. We have a reaction A, a reactant A, B, reacting with C, D, and it produces A, D plus C, B. All right. So this is our desired reaction. This is called this is our normal reactions in which these are the reactant side, reactant, and this is the product side. So the reactant side is shown as R and product side is P. Okay, so this is, we show it in this moving forward. So this is a forward reaction. And this is our normally desired, you know, in normally we desired it like that. So let's put it here that our preferred, or in other words, favorable, preferred. So favored. We found the products on the right hand side, right? So this is the right side are the products. And the left side are the reactants. Okay, and favorable means that's what we favor, we prefer, it's preferred. So all our reactions are shown this way, moving from right to left, moving from left to right, moving from left to right. All our reactions are shown this way, okay? We prefer it. But a scenario comes sometimes when AB reacts with CD and we get AD and CB, but AD and CB are short-lived. Remember, we talked about here stability. Where is that? Properties and the stability of the molecules. So sometimes the reactants are not, reactants produce the products, but the products are not very stable, right? And so that stability is very important. So here we see that the reactants, they produce the products, but the moment the products are formed, they begin to react among themselves and they go back. So we have now, this side was our reactants and this side was the products. The top one is the forward reaction or normal reaction. But the moment the products are formed, they begin to react with themselves. And when that happens, then they become the reactants. And these guys become the products. So the reactants initially now become the products when the reaction moves backwards. So forward is preferred or favorable, favored. But this one is unfavorable. That's, you know, we want, you know, we want one side. That's why we are doing all these chemical reactions. We want the products, right? So, sorry about that. Okay. All right, so we want the products, and when the products begin to react themselves, then the reaction starts going backward. So this is a situation where equilibrium has occurred. Equilibrium sets in. And equilibrium is bad because we neither get the products nor the reactants completely. The reaction is just shunting between back and forth. So equilibrium is a situation where, you know, just a useless situation. It's consuming our reactants, it's not giving the products, and then, you know, it's a bad reaction, in other words. So equilibrium reactions are also called reversible reactions. Reversible reactions. So they can be reversed. Sometimes you need that, which is fine, but not all the time, right? So reversible reactions are the ones we show them. Now, how do you show them in a graph form? Let's look at a graph. So in a graphical form, graph of an equilibrium reaction, two of them. So here is, sorry, copy and paste. Okay. All right. So what do we see here? In this case, we see this is a reaction progress moving this way. And this is again a reaction progress moving this way. And this is the reaction rate, and the other is the concentration. So here is the rate of reaction, which means the speed of reaction this way. And here is the concentration, CONCN. Okay, concentration is what? Molarity. Molarity is what? Moles per liter. Moles per liter. Okay, so that's the thing. Okay, so how do you show this? First of all, in a situation where equilibrium has set in. So here is the forward reaction, and here is the backward reaction. And right at a time where the two meet, that is where the equilibrium sets in. So this is where the equilibrium sets in. So I'm going to put EQ, equilibrium, as EQ. So in this, we are using a lot of short forms. So long words, right? So equilibrium is EQ. All right. So the equilibrium has reached at this point. So if we can quantify, where is that equilibrium, we can do something about these reactions. We can figure out like what to do, whether we should change the concentration, whether we should change the temperature, we should change the, the amount, what should we do? So let's just put this here. This is the forward reaction. This is forward, moving forward. And even for the forward, let me put there, forward is, let's put this here in another color. Forward is FWD. And then the backward is BWD, because it's just short form, okay? All right, so here is a forward, and that is FWD. And then the backward is, second, let me write this down. Backward. So that is BWD. And now I'm going to put the equilibrium is right here, equilibrium at this point. So if we know exactly at what reaction conditions that happens, or at what time, or at what temperature, or what pressure, or what the amount of heat that is given, all those things, or we know that, then we can do something with these type of reactions. Okay, and then how do you show the other piece where the equilibrium is reached when there is no further changes in the concentration of the reactants and the products? How do you show that one? So here is the products, reactants. So the reactants are going to reduce. Oh, sorry. The reactants are going to come down. And then the products are going to form. Like that. So what does the top one do? The top one is the concentration of the reactants. Remember, concentration of the reactants is in square brackets, and square bracket R means concentration or the amount of the reactants. Concentration of reactants, and that is R. That concentration means amount of reactants. And square bracket P means concentration or the amount of the products. And products are shown as P. Okay, and this also means amount of products formed. Okay, now here is the products, the concentration of the products. So products increase products increase, the concentration of the products should increase, and the concentration of the reactants should decrease. Okay, so this is what we desire. We desire that. But when their concentration becomes equal, that is at a certain point, their concentration becomes equal, and that is the situation where the equilibrium has reached. Okay, so this is the graphical representation of this. Okay, but how do you write this mathematical? So now we are going to look at the mathematical. So first of all, let's see, how do you write this? Okay, so so this also means that, let me write this down, that at equilibrium, the concentration of reactants is equal to the concentration of the products. All right, so how do you show this in a reaction now? So let us do this. A, B plus C, D is giving you A, D plus C, B. Okay, now let's put the moles. So here you have X moles of AB reacting with Y moles of CD, giving you M moles of AB and N moles of CB. Okay, this is an equilibrium. How do you show this as an equilibrium equation? So this is the equation or the mathematical representation. Equation is the mathematical representation. Mathematical representation of equilibrium. And that is always EQ. This is represented by the constant. Constant, what is a constant? So here is the constant. Constant means the when it becomes the same. So Kc, equilibrium constant expression. So expression of equilibrium constant. Expression of equilibrium constant. Okay, what is that? So here in this case, sorry, you're going to write this Kc or Keq. Okay, some books show as Keq and Kc, it's the same. Is equal to the concentration of the products. All the products are going to be on the top, raised to the power their moles, over the concentration of the reactants, raised to the power their moles. Okay, so in this case, let's do this, the top one, in this top reaction. So we have the value of Kc or Keq, means the same, is equal to brackets AD, which is the product, raised to the power M, multiply by Cb, which is another product, raised to the power the moles of Cb, which is N. Okay, then comes the concentration of AB raised to the power X, and then comes the CD raised to the power Y. Okay, so remember, these are the M, N, X, and Y are the moles. So A and D, CB are the concentration of the products. Okay, and then the A and B and CD are the concentration of the reactants. So AB and CD, AD and CB. Okay, now if the value of K equilibrium or Kc is equal to 1. What is the meaning of that? This means that the concentration of the reactants, this means concentration of the reactants is equal to concentration of the reactants is equal to the concentration of the products. Concentration of the products. Okay. This means that then in that case, the reaction is at equilibrium. It's not going anywhere. The moment the products are formed, they begin to disintegrate and they make the reactants. Next is if the value of K equilibrium is equal to, not is equal to, K equilibrium is less than 1. Is less than 1. Okay. K equilibrium or Kc less than 1. Then what happens? In that case, the reactants is less than 1. Then in this case, the reactants are more. Reactants are, the concentration of the reactants is more. So here we can say that the concentration of reactants and products is same. Okay, here the reactants are more than the products. Wait 1 second. KQ less than 1. So less than 1. Yeah, the products are less. So there are less products in the, means that less products. So let me just put this nicely. Meaning of this. So this, the top one means that the reactants and products are in same amount. Are in same amount. Okay. Next is, in this case, the products, more reactants are present and less products. The reactants are more than the products. So less products means less products. So when there are less products, that means what is the problem? Then the reaction is moving. So reaction is moving backward. Unfavorable. The reaction is moving backward. Okay, that means the moment the products are formed, they disintegrate and turn to reactants, obviously more reactants. Next is if the value of K equals is more than 1 or Kc is more than 1. More than 1. In that case, what happens? This means that the reactants are less. More products are present. Reactants. So it's very important you understand this because Le Chatelier's principle is based on that. So reactants are less, products are more. Products are more. So let's write this down. So reactants are less than the products. So this means more products. Okay, so when there are more products, yeah, it's more than one. The value of KEQ is more than one. So what does this mean? This means that the reaction is moving forward. I mean, it's still in equilibrium, but it is still moving forward. There are more products, obviously. Okay, but a little bit of the products are still disintegrating. So this is the whole premise of this thing. Now let's look at scenarios where some of these worked examples. We have 9.2. Yeah, so so this is another thing. It's the same. Reactants and the products are in same amount. So the concentration of reactants and products is equal, and this, it does not change. This concentration does not change. Okay, now let's look at the scenario 10.3 worked examples. And now we will just continue doing worked examples. Sorry, the study check. So study check 10.3. Okay, and this is page 381. Page 381. Okay, so here, write the equilibrium constant for the expression for the following reaction. So you are given 2 moles of nitric oxide as a gas, reacting with 1 mole of oxygen as a gas, stuck at equilibrium, and this is 2 moles of nitrogen dioxide as a gas. Okay, so we have the answer to this would be, the question is asking, write the equilibrium constant. So this type of question can come on the exam. Write the equilibrium, the expression for equilibrium, equilibrium or equilibrium expression. So how would you do this? This is KEQ, or you can write KC, because I'm used to writing KEQ from a long time. So the book is talking about KC, it's the same thing. Okay, products are on the top. So here you have nitrogen dioxide is on the top. Put this in a square bracket and raised to the power 2. Okay, then comes the reactants. So you have nitric oxide as a reactant, and it is raised to the power 2. That's the moles. And oxygen, multiply by oxygen, and oxygen is just 1. So for 1, we don't write. So this is the expression. So these type of questions can come on the test. All right, next look at another example, study check. Now we will keep doing this. Study check. Study check 10.4. Okay, study check 10.4, and this is page 382. Page 382. Okay, so here we have calculate the numerical value of Kc. So numerical value of Kc. What is the numerical value of Kc? If an equilibrium mixture contains 0.040 molar, okay, NH3, okay, and 0.60 molar hydrogen and 0.20 molar nitrogen. Okay, so what is the value of Kc? And the equation given is 2 moles of ammonia are disintegrating, okay, at equilibrium, giving you 3 moles of hydrogen, okay, and 1 mole of nitrogen. And these are all gases. This is a gas, this is a gas, and this is a gas. Okay, and now we have, in this case, you write down Kc is equal to, okay, hydrogen, square brackets, raised to the power 3, multiply by nitrogen, square brackets, raised to the power 1, over ammonia, NH3, raised to the power 2. All right. So you put these values of hydrogen. So Kc is equal to hydrogen. Hydrogen is 0.60 molar hydrogen. Okay, 0.60 molar raised to the power 3 times nitrogen is 0.20 molar. And since it's only one, so we don't write anything. Okay, over NH3. NH3 is 0.040 m, and ammonia is 2 raised to the power 2. Okay, so let's do this. This would mean, remember that, this means 0.60 times 0.60 times 0.60. That is the meaning of raised to the power 3. Multiply by 0.20. Okay, and over 0.040. Okay, times, because it's a square, so 2 times 0.040, and let's get this, and this is going to be the value of Kc. Okay, let's get this. Okay, so this gives you the total value comes out to be 27. Okay, so let's say the question is just moving forward, that what does this mean to you? When Kc is equal to 27, this means that Kc is more than 1. And when Kc is more than 1, it means that there are more products and the reaction is moving forward. Okay, the reaction is moving forward. All right, so this is, this type of question can be asked. Next is using the equilibrium constants now to determine, using the equilibrium constants to, to determine the meanings, like what's happening in this reaction and so forth. So calculating the reactions and the equilibrium. Okay, now we have 10.5. 10. So study check. Excuse me, 10.5. Oh God. And this is on page 386. Page 386. Okay, so you were given this reaction. C2H4 as a gas reacting with H2O as a gas, water vapor, and this is giving you ethanol, C2H5OH. Okay, when the alkene, ethene, reacts with water vapor, the alcohol, ethanol, is produced. If an equilibrium mixture contains 0.020 molar ethene and 0.015 molar, that's the water, what is the equilibrium constant of, wait a minute, if a mixture contains ethene and H2O, what is the equilibrium concentration of? Okay, so find the equilibrium concentration of ethanol at 327 degrees Celsius. The value of Kc is equal to 9.0 into 10 to the power 3. Okay, so let's do this. So first of all, you set up the reaction equation. So Kc is equal to the concentration of C2H5OH OH. This is the one that we need to find. So this is the X. You are given for ethene and for water vapor, and you're given the value of Kc. Okay, so next is, since this does not have any moles, so we will just put it as 1. So comes the reactants, 0.020 molar. That is sorry, I'm just putting this. That is the concentration of C2H4 times H2O. Okay, so here we have, let's put these numbers. Kc is equal to 9.0 into 10 to the power 3 is equal to C2H5OH. This is our, X, the value of X. The C2H4 is 0.020 m times 0.015 m. Okay, so let's get at the bottom, the denominator solved first. Okay, so first is we multiply 0.020 molar times 0.015, and that gives you 0.0003. Okay, next thing is we are going to find the concentration of C2H5 by bringing in the like terms on one side. So in this case, let me just change 9 to 9,000, 9 to 9 into 10 to the power 3 to 9,000, and you can do it on the calculator, whichever works for you. It's times 0.0003 is equal to C2H5OH, and that is the concentration of this guy. So when you multiply the two, you get 2.7 molar, and that is the concentration of C2H5OH. Okay, and remember that concentration, the units of concentrations are always going to be, remember, point, very important, note. So the units the units of concentration are molarity, that is moles over liter. And then the concentration is always shown as square brackets. So square brackets. All right. All right, now we are going to look at the next piece, which is now the Chatellier's principle. Okay, the Chatellier's principle is basically this equilibrium is of no use to us. Okay, this equilibrium is of no use to us. So Chatellier's, one second. T-E-L-I-E-R, C-H-A-T-E-L-I-E-R. Chatellier's principle is of no use. Why? Because, the equilibrium is of no use. It is not giving us the final products because that's what we want. Okay, so what do we do now? We have to disrupt the equilibrium. So he said, Chatelier said, that disrupt the equilibrium. Disrupt the equilibrium. How would you disrupt the equilibrium? By applying some stress, okay, on the reaction. Okay, now what is that stress? The stress, we will look at the different stressors, but what is going to happen? The natural response of the reaction would be to move away from the stress. Okay, that is a natural response. So this way, either you can get the product this way, either you get the products or you get the reactants back. At least it's not the wasted reactants. Okay, so this is what it is. So look at all these different stressors now we are going to do. Excuse me. So here is the conditions, different conditions. And we are going to look at the change that it is going to produce. And we're going to look at the shift or the shift in the direction of the equilibrium. Shift in equilibrium forward. So just keep this in mind that R, so once again, let me write this down, R reactants, P products, FW forward, okay, and BWD backward. Okay. All right. So what are the conditions? So first of all, let us play around with the concentration. You can change the concentrations. Concentration is the amounts of either the products or the reactants. Okay. So what happens when you change the concentration? When you change the concentration, for example, if you add more reactant, so there is a large amount of reactant. Remember, you disrupt the equilibrium by adding more. That's the stress you have applied. So the reaction is going to move away. That means move away means in the opposite direction it is going to move. So in other words, the effect is in the opposite direction. So opposite direction. You will see the response. Okay, so add more reactants. What happens? The reaction moves in the forward direction. The reaction moves forward. So let's write this down. Reaction shift in equilibrium means, let's put this here, the reaction moves, in a certain direction. Okay, so here is the add more reactants. So here the reaction is going to move forward, and when it's moving forward, that means the reaction, that means the concentration of the products is going to be more. Okay, more products are going to be. When you add more reactants, now it's quickly producing the products. More and more products will be found. That's what it means. Next is you remove the reactants. So less reactants now. So obviously you can't get the product. So the reaction is going to move backward, reverse. Okay. And when it's moving backwards, so now what is found more now? Now we removed the reactants, but now more and more reactants will be formed. So the concentration of the reactants is going to increase. Okay. Or there will be more reactants now, even though you have removed the reactants, but now the product is producing those. Okay. Next is now from your side, you also bring in, the product and add more product. Large amount of product is there. So the reaction is going to move again backward because all those products now are reacting to produce reactants. And so the concentration of the reactants increases. But if you remove, the moment the product is formed, you removed the product, then the reaction is going to move forward because you removed the product. The moment the product is formed, you remove the product. Now the response is to produce more product. So it's like it's in the opposite direction. So here is the forward direction. That means now the system will generate more and more products. The concentration of the products will increase. Okay, so that's one piece. Next is, let us look at the volume, because this applies to the gases. Okay, volume of the container. And also keep this in mind, something I forgot to mention here, that the equilibrium, this thing, what we are studying here, we are looking at the gases in the gaseous phase, where there are gases only. Okay, so this is a gas, this is a gas, this one is a gas, and this one is a gas. So always, so for now, for your course, it's just that. Okay, and then there's also the solids are also there, but for us, we are just looking at the gaseous phase. Okay, so now with the gaseous phase, we know a situation that the gases take the volume of the container. So you put them in a small container. You put them in a small container means you decrease the volume. Decrease the volume. Now here's the thing, you decrease the volume. For some reason, the volume and the moles are connected. It's the Avogadro's. So volume is directly proportional to the number of moles. Okay, so you decrease the volume. It doesn't matter whichever side, whether it's a reactant side or the product side, the system is going to move wherever there are lesser. The system moves in the direction of lesser, wherever there are lesser moles of products or reactants. Doesn't matter. Lesser moles, okay? Or you increase the volume. When you increase the volume, then it's going to expand. Then the system moves in the direction wherever there are more moles of products or reactants. It doesn't matter, but wherever there are more moles, you know, so reactants and products doesn't matter. So we just look at the moles. Okay, so whichever side is the more moles, volume will increase that side. Whenever there's less moles, the volume is decreasing that side. Okay, so that's one thing, effect of volume. Now comes the temperature. Now, if you increase the temperature, what happens? And when you decrease the temperature, what happens? Remember, increasing and decreasing the temperature, this also depends upon what kind of reaction is. So if the reaction is endothermic reaction, endothermic is already needing heat from outside. Remember that in endothermic, heat is reactant. Okay, so what happens when you increase the amount of heat? So when the temperature is increased or when the temperature is decreased, temperature increased means more heat added. Temperature decreased means less heat in the system. And since heat is a reactant, if more of the heat is added, that means more products. The concentration of the products is going to, so the reaction is going to move forward. The reaction is moving forward because now, remember, heat is a reactant. So lots of heat is being produced. So forward. And we will see more of the products forming. But if you remove the heat, then the reaction moves backward. And in this case, the moving backwards, then the reactants or the concentration of the reactants increases. Okay. On the other hand, if their reaction is exothermic, in this case, the heat is the product. So when the heat is a product, what happens? Less oh, sorry, when the temperature is increased. Temperature increased or temperature decreased. So how does that affect? So when you increase the heat is a product. So when you increase the temperature, that means you're increasing the product side. So now the system is going to move backward. So the reactants are going to be more. Next is, if you decrease the heat, that means less heat is removed. In other words, the moment the products are formed, the heat is removed. The heat is a part of a product. So the system is going to move forward because now it wants to produce more and more heat. So the concentration of the products should increase. And the last is the catalyst. So this is something, very important. You guys should take a note of these. So then comes the catalyst. Now, what's the deal with the catalyst? The increases, no effect. If you add a catalyst, there is no effect. Whether you increase when you add a catalyst or you remove a catalyst. So there is basically no effect. The only thing that can happen is that it can increase the speed. The rate of the reaction can increase. The rate of equilibrium formation can increase or decrease. Can increase or decrease. But there is no effect on, no effect on reactants, the concentration of the reactants actually, or the concentration of the products. All right. All right. Now comes the last part, which is the study check. And here we are looking at 10.6. And you are given 2 moles of hydrogen fluoride as a gas reacting with 1 mole of chlorine as a gas, and you are using 357 kilojoules of heat. Okay. Sorry, this is like, okay. So you are using to give you 2 moles of HCl as a gas and fluorine F2 as a gas. So you see all of them are gaseous reactions for equilibrium. Equilibrium reactions are all we talked about here. Where did I keep it here? Equilibrium. Okay. So in this case, we are only looking at, for your courses, the gas phase only. Okay. All the reactants in the gas phase. Gas, 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 and gas. All right. All right. Now we are looking at the study check. And here we are looking at what happens. So in this reaction, if you add more Cl2. So what happens? When you add more Cl2, means you have added more of the, that means the reactants has increased. So the reactant, the concentration of the reactant has increased. So the equilibrium is going to shift forward. Equilibrium moves forward towards the product side. So the concentration of the products will increase and it is going to be a forward reaction. Okay. Next is decreasing the volume of the container. So decrease the volume of the container. So what do we see here? We see the number of moles here. Number of moles on product side and the reactant side, and the number of moles on the reactant side, product side. Okay, so we have number of moles, how many? So let's count it. 2 coming from hydrogen fluoride, and then 1 coming from chlorine, Cl2. Okay, so this gives you 3 moles, a total of 3 moles on the reactant side. Okay, now let's look at the product side. So you have 2 moles coming from HCl and 1 mole coming from fluorine. So this alone is also C. So the number of moles is the same. So same number of moles on reactant and product side. Therefore, no effect. So you have to, this is how you calculate the number of moles. Okay. So you look at, this is, even though we do not write here, this is still considered as 1 mole. This is considered as 1 mole and this mole. So you calculate the total number of moles and then you move it. So decrease in volume, the system moves in the direction wherever there are less moles. Okay. And then the last is increase the temperature. Increase the temperature. Now, increase the temperature. So we see this is an endothermic reaction. An endothermic reaction absorbs heat. So now you add more heat. So, you add more heat. So add, increase temperature means add more heat. And heat is a reactant. So the system, so the reaction moves forward because it wants to get rid of heat. Okay, so the concentration of the product increases. Okay, so the system wants, so will get rid of the heat. So wherever there is a change in one side, the response is going to be on the other side. Okay, so this finishes this chapter. And if you have any questions, you ask me. And this is the, let me just put here. All right, guys. So thank you for watching. Bye-bye.